Hold a stone at arm's length, open your hand, watch what happens. It falls. Not maybe, not eventually. It falls, straight down, without hesitation. A child can predict it with absolute confidence, yet the stone is made of atoms that obey quantum mechanics, where superpositions are permitted and uncertainty is fundamental. How does a world built on quantum indeterminacy produce something as reliable and definite as a falling rock? That question leads to a surprisingly deep intersection of gravity, environment, and entropy, the machinery that turns quantum possibility into classical certainty. 1. Gravity without the pull. Most of us imagine gravity as a force tugging downward. Einstein replaced that picture with a more elegant idea: mass and energy curve spacetime, and objects in free fall simply follow the straightest possible paths in that curved geometry. Geodesics. A geodesic is straight when spacetime itself isn't. When you let go of the stone, nothing pulls it downward. It follows the inward curving geodesic carved by Earth's mass, the natural path through curved spacetime. But this still doesn't answer why the stone follows one definite trajectory instead of exploring quantum alternatives. General relativity predicts the path if the stone is already classical. It does not explain how classical behavior emerges. For that, we need decoherence. The universe is always listening. Quantum systems, if isolated, can evolve in superposition across many configurations simultaneously, but macroscopic objects like stones are never isolated. Air molecules bump them, photons scatter from their surfaces, vibrations ripple through them and into the surroundings. Each tiny interaction imprints a trace, a sliver of information about the stone's position or motion somewhere in the environment. This constant environmental monitoring is what physicists call decoherence. Decoherence doesn't randomly pick outcomes, it simply suppresses those quantum alternatives that conflict with what the environment is steadily recording. What survives are those histories that fit smoothly into the world's growing web of environmental clues. Gravity provides a natural path. Decoherence stabilizes that path as classical. A geodesic, the path predicted by general relativity, isn't just elegant, it's efficient. It requires no additional forces and introduces no unnecessary accelerations. That makes it easy for the environment to track. An analogy helps, though it is structural rather than mathematical. In Bayesian reasoning, one begins with assumptions, a prior, incorporates new information, evidence, and arrives at a stable conclusion, posterior. Something similar happens here. Spacetime curvature determines which paths are geometrically natural, constraint. Environmental interactions reinforce paths that match those geometric expectations, feedback. A single classical trajectory emerges as the one consistent with both outcome. This is not literal Bayesian computation, no probabilities are being updated, but the pattern of constraint plus feedback, definite outcome, is unmistakable. The downward path is the one the environment can consistently support. If you could see the air around a falling stone in slow motion, you'd witness remarkable complexity. Air compressed into a bow wave, swirling vortices in its wake, warm air clinging to its surface, sound waves ringing outward, scattered photons reflecting its position and motion. Each interaction is an entry in the entropy ledger, the physical record of the stone's fall encoded across many environmental degrees of freedom. On Earth, dropping a 1 kilogram stone from 100 meters releases about 980 joules of gravitational potential energy. At roughly room temperature, be 300 K, that corresponds to a minimum of roughly 10^23 bits of unique information, with many more redundant copies scattered throughout the environment. It's a ledger because this record is distributed widely, redundant across many subsystems, effectively irreversible, too diffuse to recompress. Entropy does not cause the stone to fall, but it ensures that once it has fallen, the world is full of traces that agree on what happened. This is how the classical world remains stable. Drop the stone in air, and its motion is continually copied into the environment through turbulence, heat, sound, and light. Classicality becomes strongly reinforced. Drop it in a perfect vacuum, and the picture changes. The stone still follows the same geodesic. Nothing about spacetime curvature changes, but there are no collisions, no turbulence, no scattering. Until impact, the fall leaves almost no external imprint. Gravity provides the same path. The environment determines how loudly the universe repeats the story. This naturally raises a question: why do geodesics, the straightest paths in curved spacetime, emerge so consistently as the classical ones? Because geodesics are paths of minimal external force. A freely falling stone disturbs its surroundings far less than an object being pushed, pulled, or thrust by engines. Forced motion shakes, scrapes, heats, and collides with the environment. A freely falling object does none of that until it hits the ground. Decoherence doesn't select geodesics through any computational process. It stabilizes whatever motion generates the simplest, most self-consistent environmental records, and geodesics naturally do this better than anything else. They are the easiest paths for the world to keep track of. Why doesn't a falling object accelerate forever? Because the air won't let it. As the stone accelerates, air resistance increases. Eventually, the upward drag force equals the downward gravitational influence. This is terminal velocity, a balance of forces. Beyond that point, no further kinetic energy is gained. Gravity continues to do work on the stone. The air continues to dissipate that work into turbulence and heat. The entropy ledger keeps growing. But acceleration stops. Astronauts in orbit feel weightless, but not because gravity is absent. At the ISS altitude, gravity is nearly as strong as at Earth's surface. They float because they and their spacecraft share the same freefall geodesic. Nothing pushes back under their feet. Nothing resists their natural motion. No environmental cue distinguishes down. Weight is the sensation of resisting gravity. In orbit, that resistance disappears. These abstract ideas connect directly to everyday experience. Why do rocks accelerate when dropped? Earth's mass curves spacetime, creating geodesics that point inward. A freely falling object simply follows this natural path through curved geometry. Why does a feather fall more slowly? Low-mass, high-area objects reach terminal velocity quickly, the point where drag equals weight, so they fall at very low speeds. Why does terminal velocity exist? As an object speeds up, drag grows until it balances gravity. After that, acceleration ends and gravitational energy becomes heat and turbulence. Are air molecules falling too? Yes, they undergo continuous micro-falls between collisions. Their collective behavior produces air pressure and support. Why don't satellites fall back to Earth? They do, sideways fast enough that their path curves with Earth's surface, keeping them in orbit. Why do astronauts float? Because they and their spacecraft share the same free fall trajectory, with no surface resisting their motion. What this essay claims: gravity is spacetime curvature. Freefall motion follows geodesics. Decoherence, constant environmental interaction, stabilizes macroscopic motion. Entropy corresponds to the spread of environmental records of that motion. The certainty of falling emerges from the cooperation of geometry, decoherence, and thermodynamics. What this essay does not claim: gravity is literally made of information. Decoherence generates spacetime curvature. Time dilation is a thermodynamic effect. Black hole physics, or quantum gravity, can be explained using this everyday picture. What this essay offers as interpretation, the way geometry constrains motion, and the environment reinforces certain trajectories, can be understood using informational metaphors. The stability of classical reality resembles a kind of selection, where only histories consistent with both geometry and environmental records survive. These are conceptual framings, not new physical mechanisms. Return to the stone resting in your open hand. When you let go, three things unfold at once. Space-time geometry determines the stone's natural geodesic. Decoherence suppresses incompatible quantum alternatives and stabilizes that geodesic as the classical outcome. Entropy spreads the record of that outcome across the environment, in warmth, motion, sound, and scattered light. You are not watching a force pull the stone downward. You are watching quantum possibility collapse into classical certainty. Watching geometry, environmental interaction, and thermodynamics cooperate to write one definitive history from countless potential futures. A falling stone is more than a familiar experience. It is a glimpse into how reality itself becomes real.